Yeah.
So Emanuele Bardacci is going to talk about the compound statistical model of the compound nucleus decay. That's a beautiful, famous picture by, yourself. Tell the story, your friend.
Bagu?
Huh? By Niels Bohr in the Nature paper. So
No, not the Nature paper.
it was in a Nature paper?
No, in a science.
Ah, in the science. Oh, right. So Emanuele, actually, before you start,
Yeah.
it's our big pleasure that you're here.
Ah,
We've been trying this for many years. Thank you, Emanuele.
Thank you so much. Actually, for me it's a big honor because I enjoyed very much my time in South Africa most of the time. Actually, I would say every time. And so I'm very happy to be here and to try to also to show what we do, but also to help to also be part of a community. And I also have good friends around here, so it will be interesting for me. So the subject of actually I try to split this subject in two lectures. Okay. So now my idea is to speak about 45 minutes. This is a typical lecture size of a class in Italy, but I'm sure it is quite a standard thing. So the subject of statistical model is quite a wide one from the let's say from the beginning of quantum mechanics, where the people realized that atomic physics started, with the Rutherford experiment. So the big race was how to study the atomic nucleus. And what was interesting at that time, that it was possible to observe transmutation. So that if we take a target of boron and we bombard this target with alpha, we can observe different kind of particle in the output channel, which is called also the exit channel. But what was interesting at that time is that if we change somehow with some mean, we increase the energy of the projectile, we observe a structure in the energy spectrum of the protons. This was quite a tricky thing because people did not know how to interpret this kind of data, and especially because at that time the most common idea of the structure of the nucleus was the shell model, something we have heard about. And there was no way to explain this data by using shell model. At the beginning I'll go a little bit slower just to introduce the subject. Then obviously I'll try to pick up speed. And so the idea is now is to start with some kind of experimental information. Okay? And then we'll try to build little by little the logic of a way to explain this data. Okay, then there are many other cases. In example, protons and aluminum, you observe gamma spectra with a lot of peaks. And you can continue. In some cases, this what is called cross-section, the number of counts of some probe at some angle, start to show even more complex distribution. In example, if we bombard proton with aluminum with protons, and we look again at protons in the exit channel, we observe something which is very interesting. It has very complex shape. But instead, if we only observe gamma in the exit channel, we observe again only one peak, instead of this kind of shape that looks like more a diffraction pattern. So the this kind of problem, it was not only typical of aluminum, it came out also with carbon. So when we observe protons in the output chart, once again, we observe this funny shape, and then we increase the energy again of the proton, we don't observe anything.
Excuse me, what is the vertical axis?
Excuse me?
What is
There is the
vertical
number
axis
of
show?
counts. Okay, at the moment, we can say how many counts I observe at one angle with respect to the beam. I fix the angles, and I change the energy of the projectile. This is called excitation function. So every time I fix the position of a detector, and I increase the energy of the projectile, whatever I observe at that angle is the number of counts. It's called also the yield of the reaction. This yield, if I keep everything steady and I only change the energy, will be transformed into cross-section. You know that cross-section is a very important quantity because it's directly connected to probability of having some reaction. Now, I'm not going to detail why we use cross-section and we don't use probability, but in principle we can discuss also about this. So this quantity here on the y-axis is proportional to probability. And what we usually use as in nuclear reaction is cross-section. Okay, so this axis is cross-section, which is directly related to how many counts I see in this detector. So if I run this experiment for 1 hour and I change the energy, for one energy I have so many counts. When I start increasing this energy, the number of counts reduce, then go up again and then reduce again and remain more or less constant when I increase the energy. Is that clear? So, but I can continue. I can take many other experimental data where I can example, this is the case of proton and aluminum. Again, here is the yield, and this is the energy of the protons. If I continue, keep increasing the energy, I observe so many funny things. Many peaks, many valley, peak and valley, peak and valley. But instead, if I use alpha, I look for alpha particles in the exit channel. I don't observe this up and down, but I will observe peaks. Again, if I only do another kind of reaction, which is exactly the reverse reaction of this one. So in this case, this is proton on aluminum, and the output, the exit channel, is alpha, and the residual nucleus is magnesium-24. Now I can switch around. I can say, okay, I try to bombard alpha particle on magnesium, okay, and then I observe protons in the exit channel. So this reaction is exactly the reverse reaction of 2, in which I switch projectile and target with residues and ejectile. And again, what I see that in the proton spectra, which is here the number of protons detected for some fixed energy, again I observe peaks exactly in the same position where I observe this for the reverse reaction. It's quite an interesting pattern. Then again, if I take alpha on magnesium, okay, so I produce exactly the same, I use exactly the same reaction, but observe again alpha in the output channel. I would call this a kind of elastic reaction, which the entrance channel is exactly the same as the output channel. I again observe these funny shapes. Clearly, this was quite a puzzle because, see, this is more, let's say, a magnifier lens. If I use proton channel, I observe these funny shapes up and down. If I use proton gamma channel, I don't observe this funny shape, I only have positive peaks. What is so?
When you say you're increasing the energy of the proton, it is the incident energy.
The incident energy, the bombarding energy.
And you observe, and the peaks that are taken, these are for the ground state now?
Yes.
Okay.
But this is something we will discover after.
Okay.
Because at the beginning, you don't know what is ground state, you know what is excited state.
Okay.
Another interesting thing that happens is that if we take an example heavy ion reaction, in which, but this can be seen also with light ion, in which we bombard a heavy nucleus with another heavy nucleus, and we look for protons or alpha particle in the exit channel, regardless anything. So we fix our detector in some position, and we look for this kind of particles. Obviously, we need to have some detector that is able to discriminate, to tell us if whatever is the signal is connected to an alpha particle, to a proton. We have also other possibilities. Indeed, we don't observe peaks anymore, but we observe distributions which are continuous distributions. This is in case is the energy of the alpha particle, this is the energy of the protons. Okay? This is not anymore what we call excitation function. Now what do? We fix the bombarding energy, okay, and observe the